Hello everyone, welcome to this video. In this video we are going to view at various examples of equivalence relations. So remember, when can we call an equivalence relation to be that whenever we have the property of reflexivity, symmetry and transitivity, right? So now in this example what we are saying, we have some set S which consists of ordered pair like this, a comma b, where what are a and b, they are integers, and this second element has to be a non-zero element. Now how do we define an equivalence relation on this class? Let's see. Suppose you take two such elements from the given set, then these two elements, they are related to each other. So this is the sign of equivalence relation, right? They are related to each other whenever we have this condition that AD is equal to BC. That means the first element multiplied with the last element, it should be equal to the second element multiplied with this first element here, right? So if that is there, these two, they are related to each other, right? So they are claiming that this relation here, whatever we have defined by all these by this line here, that give you an equivalence relation on the given set. So let's see, are we able to prove this thing? So in order to prove an equivalence relation, we are required to prove first of all reflexivity. So now what basically it means, if you take one element from S, you wanted to prove that this element is related to itself. So how it is related to itself? So for that we would say this element would be related to A and B whenever this multiplied with this, that is AB, is equal to this multiplied with this, that is BA. So you know AB is equal to BA in multiplication, because multiplication is commutative, they could change sides. So that means it is reflexive in nature. So that means the first property is there for this particular given relation. The next property is that of symmetry. For that we take two different elements. First one is this A comma B, and the second one we call it to be C comma D. Now we assume that A comma B is related to C comma D. So if that is so, according to the given property, A multiplied with D should be equal to B multiplied with C. So we have this thing there. Now for symmetry, we wanted to prove that if AB is related to CD, then CD should also be related to AB. So that means we wanted to prove that C multiplied with B should be equal to D multiplied with A. So we wanted to prove this thing. So you can just reverse the order here. You can write AD as DA and you can write BC as CB, right? No issue. And this thing would give you that CD is related to AB. So we have the property of symmetry here. For the next property, we have that of transitivity. Now for transitivity, we take three such elements from the given set. We say that the first element AB is related to CD, so that give you AD is equal to BC according to the definition that we have just defined. And moreover, we also assume that the second element CD is related to the third element EF, right? The first element is related to the second one is related to the third one, right? Now we wanted to prove that the first one is related to the third one, right? So because the second one is related to the third one, so that means here CF, that should be equal to DE, right? So we have this thing. Now using these two property, we wanted to prove that. So we wanted to prove that this AB is related to EF. So basically we wanted to prove that AF is equal to BE. So this is what we wanted to prove here. For that, we consider this thing AD is equal to BC here. We multiply it by F on both sides. Now you see this CF, you can replace the CF by DE here. So we have just done that. So this D and this D cancels with each other. So you are left with AF is equal to BE. So this is what was required in order to prove that AB is related to EF. So this give you the transitivity property for the given relation. So that means the given relation follows all the three properties of reflexivity, symmetry and transitivity. Therefore it is an equivalence relation, right? So this is about equivalence relation. Next, we have another definition, which is an important definition of partition. Now let's understand what is a partition. A partition, suppose we have some set S. So we have to divide, partition means we have to divide the set in such a way that no space is left behind. So that means when you add all of the region, you should get back whole of the set. That is, mathematically it means their union is the union of all the different portions, they should be equal to the complete set, right? And another thing, they should not overlap with each other. That means they should not have anything in common with each other. So mathematically they should mean that, it means that all of them, they should be disjoint in nature. So what do you mean by disjoint? That means their intersection, their intersection should be empty. They should not contain anything which in common to each other, right? If that is so, then we call that different portions as the partitions of the given set. So by definition, a partition of a set S, it is a collection of all non-empty disjoint subsets of S such that their union is whole of the complete set. For example, in this figure here, I have just partitioned the set into 4 subsets such that all the subsets, they are disjoint with each other. Why? Because they are not overlapping each other, and moreover their union is the complete set S, right? So mathematically you could see various examples. The first example that I have listed here is of integers. So you know this, you know about the set of integers, right? So this set could be broken down in such a way that no element is left behind. That means when you take their union, they give you again the set of integers, and those sets, those subsets, they are disjoint to each other. So the first set that I have constructed is the 0 set. Another one consists of the positive integers 1, 2, 3 and so on up to infinity. And the third set is all the negative integers. So they do not have anything in common, and when you add up all the elements, they give you the set of integers back. So this is the partition of the set of integers, right? And let's see another example here. In the another example, the set here of non-negative integers. So I have now the set of 0, 1, 2, 3 and so on up to infinity, and the set of non-positive integers. So that means all the negative integers and a 0. Now this do not form a partition. Why? Because you see, when you add up all the elements, when you take the union, they definitely give you the set of integer, but here you see 0 is the element which is appearing in both of them. So that means when you take the intersection of this set with this set, you will get 0 element. So we do not want a 0 element here, we want no element here. So we want it to be empty, that we want their intersection to be empty. So that means this does not form a partition here. Understood? And we also now can define a very important relation between equivalence classes and partitions. So basically, if you have certain set, the different partitions that you define for a given set, they are nothing but different equivalent classes. Suppose this is the equivalent class A, this is B, this is C, this is D and this is E. All of the element would be clubbed into all these equivalent classes, and moreover they are all disjoint to each other, and moreover when you take their union, they form whole of the complete set, right? This is what is there in this theorem and result that we will be discussing here. The equivalence class of an equivalence relation that constitute a partition of S. So that means if you take all the equivalence classes for a given set, they will partition your given set. And conversely, if you have some partition, right, that partition would make up equivalence relation by defining different element as different classes, as I have just told you, right? So I hope you understood about this equivalence relation, equivalence classes and partitions. So we'll be meeting in the next video. Thank you for watching.